Dear audience, dear colleagues, first of all, we acknowledge and celebrate the first Australians on whose traditional lands we meet and pay our respect to the elders, past and present. We also appreciate the sponsorship of Custom Science and Lexogen. Custom Science is the representative of Lexogen in Australia. Their portfolio includes kits for testing for COVID-19, characterizing small and messenger RNAs at single cell level and ribosomal RNA depletion kits, among others. They can help with engineering spiking controls for RNA-seq experiments. Please check out their products on the website. You will find the best solutions for expression profiling related challenges that you can face on your everyday work. Please check out one of their excellent products, QuantSeq, on the video I put into the chat. It's a pleasure to meet you online today in these challenging times. We send the warmest welcome to our friends at University of Canberra, Sydney, Melbourne, and all the other attendees around Australia. This is our fourth ACT RNA Club meeting this year, and I can't wait to hear the seminar today. This year, we have a strong focus on COVID-19 and the current pandemic situation that has significantly changed our life and still represent a serious risk for our physical and mental health. Our presenter today is Professor Peter Doherty. Peter is a laureate professor of the University of Melbourne and the patron and namesake of the Doherty Institute. He is a father of two sons and grandfather to 6 grandchildren. He is active on social media such as Twitter, discussing current political and health-related issues, followed by many of us. His primary research focus is infection and immunity. Peter has been a fellow of Royal Society for many decades, received the Golden Plate Awards of the American Academy of Achievement. He is an honorary fellow of the Academy of Medical Sciences and a fellow of the Australian Academy of Health and Medical Sciences. He has been recently inducted as a fellow of the Royal Society of Victoria. Professor Doherty and his Swiss colleague, Rolf Zinkernagel, shared the 1996 Nobel Prize in Medicine for their discoveries about a special type of T cells called killer T cells and its role in mediating adaptive immune responses and the biological role of the major histocompatibility complex, with crucial implications in cancer treatments. The work was performed at the John Curtin School of Medical Research, ANU. Besides his outstanding scientific career with more than 700 publications and 51,000 citations, he has written several books, including A Light History of Hotter, The Beginner's Guide to Winning the Nobel Prize, Pandemics, What Everyone Needs to Know, and many more. These books are joyful readings to both the scientific community and non-expert readers. He has recently published a book titled An Insider Plague Year, a fascinating walkthrough of the past year. The book has a unique personal voice, providing a deep understanding of the virus, as well as intriguing details on how he and other health experts have contributed to managing this challenge since December 2019. When it comes to great scientists, there are 2 idols that we can think of. The first one is sitting in the ivory tower and studies nature for their own beauty, cut off from the society on purpose. While the second one makes not only breakthrough discoveries that advance scientific knowledge, but also aims to influence decision-making processes to improve the prosperity and the quality of life in their country, especially when there is an urgent need to translate academic knowledge into clinical practice. Peter is a great example of the latter ideal. He broke out of the ivory tower and helped solving health and social issues such as COVID-19 and the related pandemic situation. Let me give you a quick example. Earlier this year, the National Cabinet asked the COVID-19 Risk Analysis and Response Task Force to make recommendations in order to correct and finalize Australia's national COVID response plan. The plan included vaccination targets for each phase based on and combined with the modeling of the Delta variant given by the Doherty Institute. In August, the National Cabinet decided to fully adopt the updated national plan based on the Doherty Institute's findings and recommendations. These have the following 2 main objectives: minimizing moderate and severe health outcomes and reduction of public and social measures that are disruptive to the economy and to the general mental well-being of the population. This clearly shows that Professor Doherty is not only a highly respected leader of the scientific community, but also works on enhancing the health and welfare of Australia, showing a great example to the rest of the world. At JCSMR, when I go to the lab or to my computer and pass the corridor, I never miss the portrait of him. It gives a constant motivation and reminds us that we can all achieve our dreams in academia, and that JCSMR at ANU is an ideal, well-equipped institution for this purpose. Peter is with us today, and I'm excited to hear his insight on the challenges of living with COVID. We are glad to have Professor Doherty at the ACT RNA Club today.
Okay, so I'm just going to talk for 20 minutes, and then we'll have questions. I started life as a veterinary graduate from the University of Queensland, and my interest, and I quickly went into a research environment, initially for 10 years into looking at virus diseases of domestic animals. But latterly, since 1975, I've been involved in basic biomedical research. My interest has been in viral pathogenesis and immunity. That is, in how virus diseases work, how they cause disease and death, and how the immune system overcomes them. And that's what led to the work that Rolf Zinkernagel and I did from 1973 to 1975 at the John Curtin School of Medical Research, where quite by chance, we discovered that the killer T cells, a category of lymphocyte that people were just beginning to investigate, focused on the surface of virus-infected cells by recognizing modifications in the surface transplantation molecules. Now, and this goes back to the age of the dinosaurs. This is before monoclonal antibodies. They were just being developed at that time. It's before recombinant DNA technology. So it was very hard for people to study, get the sequence of small amounts of proteins on cell surface. They had to grow up buckets of cells and then extract the protein from cell surface. So when in the late 1970s, we saw 23, 30 amino acid sequences from MHC glycoproteins, we thought we were pretty spectacular stuff. So now, of course, we sequence everything. So it's very, very different time. But my interest all along has been in the immune response. And I basically concentrated on the T cell response. The discovery at the ANU in the 1970s precipitated us into the biomedical research community, suddenly with a big reputation, but being totally unknown. And we came from out of nowhere. This is before email, so we descended on the world's population with a totally new story, which was one of the advantages of working in Australia at that time. You could really develop a story. The other great advantage was because we couldn't do most of the experiments, because we didn't have the marvelous technology of today, we could speculate massively, and we did, and we got a few things right. So basically now I'm 80 years old. I've been phasing out of direct lab involvement for about the past decade, and I'd come to the end of our NHMRC funded programs at the end of 2019. I thought I was going to retire and write more books. I like writing. And then, of course, COVID came along, and I quickly realized we were having morning meetings of our research team at the Institute. The Institute is unique in Australia. It was 5 years old in 2019. And what it is we brought together the academic Department of Microbiology and Immunology at University of Melbourne, which is a very strong research and teaching department. And we brought that together with the state diagnostic virology and microbiology laboratories, the clinical program and the medical doctors that work at Royal Melbourne Hospital, which is diagonally across the street, and deal with infectious disease, and the World Health Organization Influenza Centre. This is one of 6 worldwide and funded by the Australian government, but it's affiliated with WHO. And these are the people, now they do masses of gene sequencing of flu viruses, but these are the people who decide what will be in the flu vaccines next year. It's currently headed by Kanta Subbarao, who's a really talented and top-level virologist who we recruited from NIH in Bethesda, where she had a stellar career, but I think she and her husband just wanted to get out of the United States at that time. And it was the Institute that first got the PCR test up and going. Once the virus, the Chinese isolated the virus in December 2019. They sequenced it, And largely because of pressure from Eddie Holmes at the University of Sydney, who's a great evolutionary biologist, virologist, they published this, they put the sequence up on the database. So January the 15th, the sequence went up on the database. By the 25th, when we got our first case of COVID-19 in Melbourne from someone who'd come across from Wuhan, we had the PCR test running. It was up and away, and then we diagnosed the first case, isolated the virus from the first case, and were the first to distribute the virus worldwide. Now, that's really important. You need infectious virus so you can do virus neutralization assays, which are the absolute benchmark test for virus-specific antibody, and also so you can do virus challenge experiments in animals and so forth. And so from then on, we were having 3 times a week morning meetings, and where all the heads got together, and I was asked to join those. So at that stage, I'm just working 1 day a week, which I'm still doing, but I seem to be working about 4 days a week or 5 days a week on COVID. So what I quickly realized from listening to my colleagues, we'd meet from 8:30 to 9:15 in the morning, 3 times a week. Even at that very early stage, and I'm talking about March 2020, people were getting exhausted. And the reason they were getting exhausted is they were all spending a lot of time online at webinars, at committee meetings, and speaking in the small hours of the morning in Europe and North America. So it occurred to me, because I've been doing science communication since the Nobel Prize back in 1996, I got drawn into trying to talk to the public about how science works. And that's why I started to write books, with the first one being published in 2015. The latest is the one that's basically about that first year of COVID from our experience. And basically, I'd done a lot in the public space. I'd learned how to talk to people in the public space. I was on Twitter, but I had very few followers. I think about 16,000, but not a major thing. So I decided, listening to my colleagues, I was no longer running a lab. Catherine Kizierska, Steve Turner, Nicole Legritta, both at Monash now, and Catherine at the University of Melbourne, had really taken the program that I'd sort of started with them as postdocs back in 2002 when we came back to Australia from the United States. And they're now all 4 professors and running great research programs. Catherine recently got elected to the Academy of Health and Medical Sciences. So I decided what I would do is, rather than get in their way, because there's one thing that old scientists should not do. Firstly, they should not use resources, which should be there for young scientists. And secondly, they should get out of the bloody way and not disturb people and try and run things. Because old scientists who hold on to power are a disaster. I mean, I think Isaac Newton said it way back. Science advances by funerals. Well, you need to kill yourself off. So I decided I'm taking myself out of that. I'll do science communication. And I also decided I'd do it for the stuff, not the really prominent stuff, not the Q&As and all this stuff, because I wanted our younger people, and younger to me, as you know, 50 or 60, to get a high profile on media, because scientists, at least in leadership roles, it's helpful now if they can have a media profile. So I got out of that. So I started doing the science communication stuff. I've done lots of interviews, and I started writing a weekly column on our website, a blog called Setting It Straight. And so I'm doing 800 or 900 words a week. I'm now up to numbers. I'm due to start writing number 76 tomorrow. I can tell you this is hard work, writing a weekly column. It's really a slog. And for an old guy like me, who's unreliable and undisciplined anyway, I've got to really keep myself to it. Okay, so COVID-19. So this virus comes along. For the past 30 years, the main virus we've worked with is influenza. And I used that a lot. After the Nobel Prize was awarded just as the tetramer technology was introduced. And this is basically, you make tetramers of the MHC glycoprotein with peptide attached that combine to the T cell receptor, and you can fluoresceinate them or whatever, which means you can actually identify the individual cells in the cell sorter, and you can sort the cells and look at their molecular profiles, particularly initially mRNA, But latterly, of course, we're looking at everything, including the regulatory genes and all the rest of it. So you can do enormous things with a single cell. Now, this has revolutionized human cellular immunology. Most of the work I did within mice, Catherine Kizierska has transferred that mouse work into humans. But what you can do now, it was very difficult to do cellular immunology in humans, particularly in pediatric situations, because it was so hard to get enough cells. But now you can take a single cell and you can do great science. So that's why medical science has become so much, that together with all the other advances in molecular science, is why the human has become so much more at the center of medical science than the lab mouse. So I represent that earlier era. I mean, my MD is a mouse doctor, but basically now you can do wonderful things collaborating with your medical colleagues, or if you have a medical training yourself, actually working in these situations and looking at patients. And we really need that, particularly in, say, COVID. We need to look at long COVID. It's a really mysterious phenomenon, and we don't understand that well at all. So basically, when COVID first hit, we were saying, well, this is not influenza, because we all had SARS-1 in mind. And we said, but we were thinking of it like influenza. We were thinking of it like a bad flu. I mean, the mantra with influenza is you can't stop the flu by stopping the planes. I've been to hundreds of flu meetings where that's been said. You can't stop the flu by stopping the planes. Well, the original Wuhan strain of this virus was as infectious as flu, it had the same R naught. And so we know you can stop these viruses by stopping the planes, because we stopped that virus. Now, it's much harder to stop Delta, because Delta is about 3 times as infectious. It shows the infectivity of basically chickenpox. Now, that won't mean anything to you, but it does to me, because even my kids got chickenpox. It was pre-vaccination. So that's a highly infectious virus. And as you can see from both New South Wales, Victoria, and the ACT, we're having the greatest difficulty hammering this thing down using the techniques of lockdown and so forth we did before. Effectively, in New South Wales and Victoria, this virus is already out and away. We're not going to bring it down to 0 again. And basically the whole opening up thing, it's a matter of whether we open up or it opens up us up. And we're going to have an element of both with the planning and stuff. So I started writing about the basic science of this, because I didn't want to replicate what the journalists are doing. They were giving good accounts, and basically the journalism has been pretty good on this, right across the spectrum, from the left to the right. But I started to write about the basic science, tell some stories that might amuse a little, so people could actually, who wanted to know what this actually means, could actually look at it and come across it in some fairly amiable format. Now, though I've written I'd written 6 books on science and the scientific life, I'd always avoided my own subject of infection and immunity, because it is so complicated. Firstly, immunology is an extremely complicated science. And secondly, you interface an infection with that, you get into another whole area of complexity. But now I've been forced to do it, and that's that book actually includes the first 42 of those essays, which explains a lot of those basic things. So we're thinking of it like flu. It seems like a bad flu. And then suddenly, and I think it was about May, a pathologist in New York said, and we were thinking of the fact that people are struggling for oxygen is flu, because the virus gets into your upper respiratory tract, then your lower respiratory tract. In flu, often with the help of big, powerful cytokine responses, all these toxic chemicals we make early in infection. And if we don't clear the infection with this specific or adaptive immune response, these can keep coming along at a high rate. And that's one of the treatments actually for people who are hospitalized, to damp that down. With dexamethasone or with antibody to IL-6 or something of that sort. But in flu, they can cause basically vascular leakage, and you drown in your own lung fluid. So we're thinking this is what COVID is doing, but it's not. It's doing a bit of that, but that's not the main problem. The main problem with COVID is, unlike flu, flu stays in the lung in humans. Unlike flu, this virus gets into the blood. It's what we call a systemic infection. It's viremic. The virus gets into the blood, it goes around the body in the blood. Once it's in the blood, it can access all the body organs. There's the blood-brain barrier, and we don't know how much virus gets into the brain. There's clearly major brain-related problems due to in the long COVID phenomenon, but we don't know how much that's due to virus in the brain. So the virus gets into the blood, and it triggers the clotting cascade, which is triggered through the liver by hormonal type pathways, but also it gets into the blood vessel walls because it binds to ACE2, which is a very ubiquitous molecule in the body, and it binds with extremely high affinity, and it roughens up the surface of the blood vessel. Now, if you've got significant flow through a roughened surface, you'll get clots, and you get blood clots. And when you hear of, say, a 20-year-old suddenly dying of COVID, they're probably dying from blood clots. They're probably having a stroke or a heart attack due to a major blood clot, okay? But the other thing, which is even more hideous to a pathologist like me, I started my career looking down a microscope, even more hideous, you get micro clots in the little blood vessels where the blood gas exchange occurs in the terminal alveoli of the lung. The little microcapillaries there, you get these microclots and you block the gaseous exchange. And that's what kills people, is lack of oxygen. You die from lack of oxygen in flu too, but you die from lack of oxygen in this because because of this, principally, I think, because of this clotting problem. There's also some of the other as well. There's horrible lung damage in this. It's what's called ground glass lesions. That's what the images see. It looks like ground glass, and they look really hideous. They do resolve rather better than one might expect, though. Now, so that was the clotting issue. We suddenly realized, and now, when someone goes into hospital with COVID now, they're anticoagulated. They're given low-dose heparin, and they're given dexamethasone to decrease the inflammation as the thing goes on, if they're in. Now, if you're vaccinated and you get a breakthrough infection, which can happen, and you end up in hospital, you may be in hospital a couple of days, unless you're really old and you're frail and your immune system is just crap. And of course, that's what happens with age, and then you may die of it. Double vaccinated people die. 95-year-olds, 85-year-olds can die, even though they've had 2 shots of vaccine. But mostly, the vaccines work actually really well in the elderly for vaccines. In fact, they're extremely good vaccines. So that's kind of the story of the pathogenesis. But then on top of that, you've got this hideous long COVID effect. Well, and this is really poorly understood. The neurologists and the infectious disease physicians for years have battled with this syndrome that people come in with, particularly women, and of what we call chronic fatigue, chronic muscle pain, and so forth. Haven't known what to do about it. They've realized this is real. It's not psychosomatic, it's real. These people are genuinely suffering, but they don't know what to do. Now we have a virus trigger in COVID because we PCR test everybody in Australia. So we've never done this before for any infection. We've never had a specific diagnosis for a disease which maybe is asymptomatic. So you get a PCR positive, and then with some cases, people are totally asymptomatic. Some that have mild infection, we would never pick those up normally. They'd never go to the doctor to be diagnosed, right? The ones with severe infection would. So we'd pick those up. But we pick up the asymptomatic and the mild infections. And some of those, some of the asymptomatic, some of the mild, go on later to develop this long COVID. And long COVID hits people of every age group, not just the elderly. The elderly are likely to die. And the people who've got other compromise, particularly diabetes, because the virus is in your blood, it can zap your kidneys, and diabetics have crap kidneys anyway. So what will kill people when we open up and when our hospitals get under massive pressure? Some people will die because there won't be enough dialysis machines for them. That'll be almost certainly a fact. So basically, long COVID is the thing that's really concerning. We don't yet have clear, long COVID is very difficult to unpick because people are largely self-reporting it. You're not sure there's a proper diagnosis in the first place. And it really, it's fortunately being studied in some very well-controlled studies. There's one at the University of New South Wales run by Tony Keller out of the Kirby Institute called the ADAPT trial, which is really good. There's clearly an immune dysregulation. There's clearly something going on in the brain, though we don't really know what. And it could be the microglia and the astroglia are sort of activated, whatever that means. And there's inflammatory changes. There may be neurohormonal effects. There may be autoimmune effects. We don't know. And this is going to take some unpicking. But now we're suddenly starting to see that you can, we may be able to unpick this whole chronic fatigue thing because we have the specific virus trigger and we can follow the disease. Now, basic message for everyone, of course, is get the vaccine and get it when you can, because you don't want to get long COVID. It's not clear that, in fact, it's possible that the vaccination doesn't completely stop long COVID. You do get breakthrough infections with the vaccine. Vaccinated people can transmit. That's not surprising. It's easy to keep antibody levels high in the blood for a vaccine you give in the arm. If you go to our Setting It Straight series, a couple of weeks ago, I did a little hand waving exercise on how the vaccine works, and that sort of a simple explainer. So you can keep antibody levels high in the blood. It's pretty hard to keep them high up here. What you've got is a totally inert particle, the virus, tiny, inert, bit of nucleic acid with some protein and lipid and sugar around it. And it's just drifting around. And then you've got the antibody molecules, which are just molecules, a Y-shaped molecule. They're just drifting around. And you've got to get the antibody and the virus together in the nose. And they're in the blood, but there's not that many of them in the nose when you give the vaccine here. And you've got to get them together before they hit that ACE2 molecule. The virus gets into the cell and gets away and replicating. So people get infected up in the nose. Some vaccinated people can get pretty ill. Most won't go to hospital. A few do. They don't usually stay too long. People are in ICU for a very long time with Delta, unvaccinated people. And basically, though, once it gets into the blood, I think, the antibodies are there to handle it. And that's why I think though you can get symptoms as a post-vaccination situation, you don't normally get this really bad long COVID. So we're hoping we won't see bad long COVID in vaccinated people. Certainly because even if you take the symptomatic people who get a breakthrough infection, and they're a great minority in the breakthroughs, I think the ones who get long COVID may be about 20% of those. And we don't know how long because it's too soon and because we just don't have those really good defined case studies and series that people are looking at systematically. So a lot of research to do here and a lot of working out to do. So that's a bit where we are with COVID. Of course, the whole opening up scenarios that everybody can get into the modeling, which is the so-called Doherty modeling is actually Jody McVernon's team. It's people from 5 other universities as well. They're really terrific, but in the end analysis, models, whether they're climate models or financial models or whatever they are thought experiments. They're only as good as the parameters you put in. And some of the parameters are very, very soft. For instance, the degree of transmission from vaccinated people. So, they've inherently got issues. I tend to think of modelers like spies. The head of the CIA, except when Trump was president, because you couldn't tell him anything because he'd tweet it. The head of the CIA normally goes into the president's office once a week and says, "Mr. President, this is where we are. This is how far you can go in that direction. This is how far you can go in that direction. And you've got to make a choice between those." And that's what modelers do for politicians. Scientists don't make policy, politicians do. That's their job. And I really wouldn't want to have it. And I even feel a bit sorry for some of them and having to make some of these decisions that are coming up because they're really tough decisions. Anyway, that's where I'll leave it. And if you want to ask any questions about COVID or anything else, I'll do my best to answer.
Many thanks, Professor. So questions from the audience? So I will seize the moment and ask my question. So what do you think the best solution would be for the long run? So should people be vaccinated on a yearly basis or on a 2-yearly basis and on a voluntary basis, or should be?
Yes. What we're seeing with COVID is the vaccines are all against the original strain, the Wuhan strain. What we can see is that antibody levels are falling. And that happens in all infections, basically. You get an infection. What happens is when you get the infection, it goes into your arm, it gets into your regional lymph nodes, and that's pretty much where the immune response happens, in those regional lymph nodes in your armpit. That recruits loads of white blood cells from the blood to find the rare ones with the right specificity on their surface, B cells, T cells, and all the rest of it. And they drive into proliferation. So they'll divide every 6 hours. So if you've got cells dividing every 6 hours, you'll realize that in 6 days or so, you've got a hell of a lot of cells. Now, some of those cells will become memory T cells and B cells. Some will become effector cells, the killer T cells, for instance, that go and bump off the virus-infected cells, which are the virus production factories. And some of them the B cells will localize in bone marrow, differentiate to form plasma cells and pump out antibodies. Now, the Delta strain, I don't think it's an immune-selected variant. I think it's simply a better growing variant. It first emerged in India in December 2020, before any vaccine was in use, and before enormous numbers of people have been infected. So I think all this variant is following the basic principles of evolution. All a virus does is multiply and transmit. That's its evolutionary strategy. So basically, the faster it grows and the higher titer it grows, that virus will take over. And that's what Delta is. It's a faster growing, higher titer virus, which takes over and it displaces the other viruses. So Delta is handled about a third as well by the antibodies to Wuhan. It's still handled, which is really gratifying. It's not like flu, hasn't changed completely. These viruses don't mutate at anything like the level of flu. They do mutate, and we can follow those mutations through as a kind of barcode, which allows us to do the genomics. When this thing started, our bacteriology diagnostic outfit, the MDU, Microbiology Diagnostic Unit, switched. It had got a new chief who dumped all the old stuff they used to do or put it more in the background and bought big sequencing capacity. And so what they were doing sequencing of all the streps that causes those horrible skin disease and all the rest of it. But what he did is switch some of his capacity to do the sequencing on the COVID isolates, the SARS-CoV-2 isolates. And so then we've started really this whole field of genomic epidemiology, where you can say this cluster came from there, that cluster came from there. At the moment, I think in Australia, it's only Delta that's circulating, but you can see some substrains that have emerged because they've got minor mutations in them, not significant, but minor. So we can trace these various lineages. Now, I mean, it's really the mRNA vaccines that are tremendously exciting. I mean, people have been working on these for decades, but actually seeing them come through in the way they did is spectacular. And now, of course, people are talking about all sorts of other applications for RNA, mRNA intervention in clinical settings. And then we're hoping we'll develop a really significant industry here. The federal government is committed to the mRNA vaccines, but no, it'll have to go further than that. So we're hoping that we can really build something here in that area.
Peter, Kerry Mills here. I'm just wondering how you see the role of PCR as a diagnostic tool in the future, given that we have now, like very poor correlation with the end of infection and being able to pick it up with PCR. So people are,
as you know, you pick up PCR product. So you're not picking up
so you're not testing.
So early on, you'll get really low cycle numbers, which says, there's a lot of virus around. That's pretty valid. But then you're picking up PCR in sewage product. So basically you're picking up there's some nucleic acid there. Yeah. Incredibly sensitive that you can, we're using the sewage testing a lot. In fact, Peter Doherty from ANU has been a great fan of this.
Yeah.
Yeah.
My question is so there's actually fairly poor correlation outside of this in unvaccinated initial peaks. So if you have a person who's vaccinated and they get infected and the viruses in their body are coated with antibody, those virions are not infectious anymore. And yet you would test...
all the PCR is done up here.
Yeah.
We don't normally do blood. I mean, you can do blood, obviously, because that's how we know it's systemic. So it's basically up here. So how much antibody is there? Certainly you've certainly got a lot of infectious virus up here, including in vaccinated people. And that's been done.
Mm-hmm.
But of course, as you say, some of it may be coated with antibodies, so it's really out of the equation. And we think, I think there's reasonable evidence that it can grow to just as high a titer initially in vaccinated people, but that it will be there for a shorter time and infectious for a shorter time. So we think vaccinated people, though they can still transmit, and many clear instances where they do, we think that they will transmit for a shorter time. But this is a lot more infectious than the original strain too. So they are a significant factor in the transmission. And of course, as more and more people get vaccinated, we're going to see this more and more. I mean, when we're talking about 80% vaccination, we're talking about 80% over 16. That was the modeling that the government requested from our people, over 16 for 6 months. So that's what they got. As you know, modelers deliver what they're asked to deliver in terms of the strategy. So basically, even if you take that down to 12, and if kids are being vaccinated down to age 12, my youngest grandson signed up, for instance. So we still have 3 million unvaccinated under 12s, and they can transmit as well. Early on, kids weren't bringing this into the household, so we weren't so worried about the schools. But now it's clear they do bring the virus into the households, and more of them get infected because the virus is more infectious. Not very clear that it's more severe disease in kids, but because more get infected, we do see more severely affected kids, just on the proportional basis. Yeah. So there'll be 3 million unvaccinated kids when we're at 80%, and then we've got another 4 million unvaccinated adults. Varying levels of intellectual capacity. So, there's a lot of people there to spread the virus. So I think, PCR, the other, we haven't used the rapid antigen tests much yet. These are what we call lateral flow tests. They're 15-minute tests. Still have to stick something up your nose. You still put it on in a bit of buffer and you put it on the slide, and then you look 15 minutes later. These can be made really pretty quantitative, actually, but if you've got a proper reader, and they can be they're reasonably sensitive. PCR is more sensitive, but as you say, you're not necessarily picking up infectious virus. I think we'll see a lot of them rolled out a lot more as we sort of look at, say, maybe you need to do one of these and test negative before you go to a construction site or go and work in a hospital or a school. So we'll see what happens there. They're only about $5 a shot or something.
Thank you.
Nikolai has the following question.
Thanks so much. Thanks so much, Professor Doherty. It's an absolute pleasure to listen and to communicate. And of course, as somebody who works at JCSMR, I get inspiration from your work and life path on a daily basis, really. And just to note before I ask a question, that there are also some, I think, very good questions in the chat. But first, I would like to quote actually you and see if your opinion changed over time, because it's a citation from some time ago, and that's about your answer on about conceptually driven research. So conceptually driven research, that's a direct quote, as opposed to end-user driven research, is what is likely to yield some of the biggest benefits. But with this stuff, you can't be sure whether it will end up. Real curiosity at work can be confined by a short time horizon and doesn't guarantee an outcome. Plenty of research leads up blind alleys, but you have to know that those blind alleys are there in order to find the right path. Just to quote this, because I always also get inspiration from that, and just to get your view, if how are we doing again? Sort of, following this.
Yeah, I think one of the really interesting things that's happened with the sort of evolution of the molecular medicine era. I mean, there's always talking about mRNA vaccines, for instance. I mean, there's discovery, but then there's obviously a lot of downstream work. Really requires highly skilled people and people with a lot of insight, but to actually make things work. And as we know that from the mRNA vaccine story, it's the people who sort of got the lipids right and so forth that are really important in this story too. So there's all that sort of research. And now, so the differences in my experience as a scientist is Zinkernagel and I won the Nobel Prize for two young guys in a lab who were largely, for various odd reasons, pretty much unsupervised. I already had my PhD and I published about 25 papers, I think, in the veterinary world. And he was just starting up. But there were two of us with a not particularly competent technician, and we won a Nobel Prize for the experiments we did. I mean, that doesn't happen like that anymore. I mean, it's bigger groups and interactive. And I think one of the great things about science, of course, is the collegiality of a good lab. Being able to talk and throw things backwards and forwards, and that whole excitement of being in a good institute. Like the John Curtin School, as it was then, I'm sure it is now, or our institute, where you can throw things around and you get them thrown back at you. Now, but what we've seen, for instance, is Ben Howden, who runs the diagnostic unit. He's a medic, but he's doing massive amounts of gene sequencing. And there's a whole new sort of research, the genomic epidemiology stuff, but there's a whole new stuff coming in from there. So I think those divisions between what we used to call pure and applied, I abandoned that one a long time ago. But I think with molecular science, you can go from discovery to sort of starting a biotech, I mean, very quickly, which is what I saw happen in the US. I was in the wrong field. I'm a cellular immunologist and never really was in that. But some of my colleagues have made scads of money by sort of making that jump. So I think there's not that, in a sense, that we need to be able to follow that line led by curiosity as we try to dissect mechanism and we try to find new ways of doing things. But it blends very much, I think, backwards and forwards between the more practical and the more intellectually driven, if you like. And so I think other fields have been in this stage for a much longer time than us. Obviously engineering, but elements of physics, chemistry. And now, of course, we're all working with chemists and engineers, and we're not just working with other biologists. It's a very, very different scene. We've all got statistical guys who are doing the informatics, and they're driving a lot of it because these data sets are you just can't look at them and analyze them. You have to have the informatics approaches. So it's a very different type of science, very satisfying, but it's getting more like experimental physics, where you've got large groups of people who are sort of driving things forwards. But you still have the Dudner and Charpentier, for instance, who really drove that through and made it work. Really wonderful story, couple of wonderful women, really.
And a little bit more scientific question that I have is, so we're in a very unique situation with the COVID, and because it's like a lot of people, it affecting really entire population, we can say that, I guess, in the world population, but it's also medically addressable. So we have tools, and really, I guess, the vaccines that we currently have, they won't be the last ones, and there will be a lot of development, a lot of fighting also, which one is better perhaps. But it also probably will result in that we actually eliminate, or we find much better cure to many viruses that were thought kind of, before. But my question is, even after that, whether we will need to study or actually, invest into understanding whether these viruses actually play a role in human development, because no human develops without its needs. And while we know the genetic implications of some of these things, that some of them, affect genetic mobility and perhaps help on a longer evolutionary scale, the developmental effects, I'm not sure that they are fully understood at the moment. That would be my question.
I think the evolution of our immune system is basically a back and forth between infection and the evolution of immune responsiveness. And clearly viruses have played a big part. And if you look at particularly the herpes viruses, big DNA viruses, or the pox viruses, and you look at them from different species, with viruses that don't infect the other species, I mean, they were single species specific viruses, you will see that they all have some type of molecular strategy for avoiding T-cell recognition, either by messing up the MHC presentation or antigen processing or something. Different strategies that achieve the same thing. So you see convergent evolution pathways to achieve a particular end, but actually working in different ways. It's quite fascinating to do that. And that's one of the areas where you would kind of struggle to get funding in a grant. I mean, unfortunately, evolution is not necessarily all that easy to fund. But I think if you're thinking of COVID, for instance, if you look at this, and I mean, COVID really is teaching us all about the interplay between human behavior, infection, and all the rest of it, which most of it, those of us who are older became very aware of with the AIDS pandemic in 1981. We were forced to confront this, that it's a behavior-driven disease in many respects. So basically, it's telling us a lot of things. But if you look, before 2000, there were 2 human coronaviruses circulating. The common cold and croup viruses. They were first discovered back in the mid-1960s. That's when the first corona was described. The term corona was given to the virus by a Scottish electron microscopist, Jude Almeida. She was Scottish. She married someone called Almeida and got rid of that guy, and then ended up in London doing electron microscopy. So it was named by a woman, the coronavirus, when she first saw those coronas. And so we had 2 circulating before 2000. Since 2000, 5 have come across into the human family. There's the original SARS, which burnt out. There's 2 new common cold ones. One of them may have been circulating before we missed it. There's MERS, the Middle Eastern one, which goes from bats to camels to people. And now we've got CoV-2. So 4 of those viruses are still circulating, plus the 2 from before 2000. So there are now 6 coronaviruses in 2020, where we had 2 in 2000. And so what's happened here? Well, I think nothing's changed except massive increases in international passenger air travel out of China. I think a lot of these are coming across through live animal markets. I think basically the flu's come across through live bird markets. These are very, very dangerous operations. And I think the Chinese have to work out how to handle these in a more controlled way if they're going to keep up that cultural practice, which is well embedded in their culture and so forth. So that's part of the issue. And of course, if we hadn't been thinking of the flu mantra, that you can't stop these viruses by stopping the planes, maybe they would have stopped those planes out of Wuhan early. And I think we need to do that. I think in future, we need to stop the planes. We need to have notification, total openness about notification, World Health Organization strengthen and stop the planes. The other thing that's happening is no matter what we do, and we can probably shorten the time it takes to make vaccines, especially with mRNA, as we've gained a lot more experience with it, but it will still take months, 6 months, 9 months to get a vaccine out there. And you've got to ramp up your production and all the rest of it. So I think the other thing we can do is the antiviral drugs, the small molecule drugs against influenza, work really well if you give them just at the beginning of the infection, which we wouldn't normally pick up, but we would pick up if we were doing PCR diagnosis. So the antiviral drugs for flu work against all the flu viruses. The antiviral drugs for HIV work against all the HIV variants. So now there's a big NIH program to make anti-coronavirus drugs that work across all the coronaviruses and the other viruses that are potential threats, like the Henipaviruses, the Nipah Hendra group, the filoviruses, Ebola, Marburg type group, and so forth. So I think what we need to get these antiviral drugs made, get them tested, and we could test the coronavirus ones by doing, say, human challenge experiments with the common cold coronas. That'd be perfectly legitimate, and get them licensed, approved for use, and get reasonable stockpiles made, which could be deployed immediately. We get one of these events.
Thank you very much. So the next question from the chat. So from Rhiannon Nielsen, I'm part of the ADAPT study. I was infected in March 2020, and I had to take 3 months off my PhD because of long COVID, specifically fatigue. A question for Professor Doherty. The ADAPT study found that my antibodies correlating with the nucleus of the virus diminished over the year, but the antibodies correlating with the spikes in the virus were naturally increasing in my body. What might be the case?
Yeah, interesting. We're really grappling with this. And well, Kelleher, for instance, is at Sydney. Is the virus persisting in some way that we're not finding? You know, people with this, fortunately, are not commonly coming to postmortem. And of course, we don't do postmortems in the way we used to. I mean, you'll see them on TV with CSI and so forth. These are in crimes, postmortems get done, but in medically, we're doing many, many fewer postmortems than we did in the past. So in a way, it would be better if we could particularly to look more on the brain. But basically, so what does that tell us? Does it tell us the virus is persisting? Another possibility is viral protein is persisting on the surface of things like what we call plasmacytoid dendritic cells. So we don't really know. And a lot of the debate is, well, is this autoimmune? Are we triggering some anti-self response? I don't think there's good evidence we are yet. Or is it persistence of the antigen? Because as long as you've got that antigen in there, protein or virus-producing protein, you'll continue to drive immunity. And so that's one of the first questions that really needs to be answered. I hope you're fully recovered now and that you're feeling fine, because a lot of the issues about long COVID is how long. And for some people, it seems to be pretty permanent, which is terrible.
Tanya has the next question.
Well, thanks, Attila. Peter, thank you so much. That's very, very interesting so far that you've been talking about. I have a very, I guess, specific question about COVID. I'm quite concerned about how Australia is now jumping into vaccinating 12 to 15-year-old children with Pfizer vaccine. Especially now, there are some, med-archives, preprints coming out showing that the prevalence of this heart inflammation in adolescent boys is quite high, 1 in 6,000. And in comparison to obviously heavy disease with COVID, hospitalization of kids, 12 to 15-year-old boys, especially it's more prevalent in boys, the reaction to vaccine. The COVID disease itself, only, bad cases are 1 in 50,000, 1 in 25,000 cases. And yet TGA has approved double dose for Australian kids, while we know that UK, for example, and Israel, they only decided to do one jab for the 12 to 15-year-olds, and Germany and Norway decided not to do this vaccination just yet. So what is your take? What do you think is the best strategy for vaccinating our children?
So you got to figure 1 in 6,000. Where did you get that from?
So that was a medRxiv preprint
Okay.
on 13th of September. It came out, they said recently, they said 162 cases per million. So that translates into 1 in 6,000.
Okay, I need to look at that. I haven't seen that. Yeah, I mean, it's, basically these questions, to my mind, are up to the pediatricians and the parents and the government and the regulators. So basically, I don't, as a vet particularly, I have to stay out of medical advice. But really, there is also another mantra in medicine that, and this comes in particularly with the use of the immune checkpoint inhibitor monoclonal antibodies against cancer. And it's a very different situation because people would die of melanoma. But the doctors can handle the autoimmune disease problems that come out of this. And so they go for there. So the myocarditis problem, as I understand it, kids can be hospitalized for several days, but pretty much people come out of it pretty well. And it is myocarditis, it's not myopathy. I mean, myocarditis is inflammation. Inflammation resolves once you take away the trigger. And my understanding is this is resolving quite well. And of course, if they do get COVID, the cardiomyopathy problems that are potentially following COVID and long COVID are really, it can be very severe, and in kids of that age too, and certainly in young adults. With, it's really most of the people in hospital in Victoria now are under 50, because the oldest are probably more careful, and they're also double vaccinated. So it's a bit of a trade-off. In general, I'm sort of comfortable with down to 12, but basically we'll have to see what happens in the younger age groups. And there's been some discussion, I think, of cutting the dose, the second second dose and stuff.
Yeah, well,
so I guess you've got a 12-year-old and you're really concerned, but it is, I think, something that parents will need to look at, and they'll need to have good, clear information. But as I understand it, in Australia now, we've had 9 deaths from AstraZeneca due to that horrible blood clotting problem, which is a really complicated issue. And I don't think we've had any deaths from Pfizer, though the people will tell you that that hundreds of people have died because they look at adverse incident reports.
Yeah, that's
so, you know,
yeah.
and it's crazy, and you can't get them off this. And so you vaccinate millions of people. Some people are going to get sick, and some people are not going to be good. Yeah. So no, it's a good question, but.
Yeah, I just don't understand why they didn't try to do 1 vaccine, why they're mandating now 2. And that means if a child gets only 1, they'll never going to get the passport, they'll never going to be able to travel later on. That's something that
right, I understand. Yeah, I don't know. I mean, it's certainly, I'll take it up with some of my colleagues and see what the discussion is. Yeah.
Thank you, that would be good. Thank you.
Okay, next question from the chat. Would a nasal or inhaled vaccine work better against COVID? And the same person asking another question that, do you think that the lethality of SARS-CoV-2 is linked to the lack of adaptive immunity in the global population? For example, if we had been exposed to this virus in childhood, would it then not have any problem?
No, I think that's absolutely right. I mean, once this thing becomes endemic, which I think it undoubtedly will, it'll become less of a problem. And people talk about that, more flu-like. You know, even though we change the flu vaccine every year, because the flu virus has mutated at a hell of a rate. And still, even though they mutate at a massively higher rate than COVID, we really only select 1 variant each year at the most for each of the strains. So basically, there's a background of immunity to flu, and that is the T-cell immunity, the stuff I worked on. That's not immediately there because you have to recall T-cell immunity. You have to get the cells back multiplying again. But it is there, and I think it does protect us to some extent. And it may be why we haven't had any really terrible flu pandemics, because with planes flying all around the planet, flu gets around the planet very quickly too. And so we may be all keeping pretty highly primed against flu. So that may be the eventual fate with COVID. You know, when people are talking about a 3rd booster now, at the moment they're talking about a 3rd booster with the Wuhan vaccine. So that's virus antibody levels are declining, and it probably handle the original virus all right, but not handling the Delta as well. So we need to boost them up again. So that's the 3rd. But of course, the currently Pfizer and Mrna, I think, are both working on Delta variant vaccines. So they might be the booster vaccine next year. Now, maybe people of my age will get a booster shot because I think it is genuinely beneficial in older people. So yeah, it's. I think we will see this come to be a more, and this may be what happened when those other viruses came across early. Though the 2 common cold ones that came across this year were not severe infections. The original SARS, on the other hand, kills 10% of people. This virus kills 0.8 to 0.3%. Really, we thought it was much higher initially because people were reporting death rates from clinical cases, but there's a lot of mild and asymptomatic infections, especially early on.
Thank you very much. Next question from Hardy. How do you think our health systems has changed due to the COVID for monitoring infectious diseases? What is the role of DNA sequencing technologies in the future surveillance of infections?
Well, I think we'll be sequencing everything from now on pretty much as part of the surveillance mechanism. Now, whether we do, say we got a really bad flu outbreak, would we set up universal PCR testing again? To test everybody and then give them drugs straight away. I mean, that would be a possibility. You'd stop the outbreak, because if you give, say, Tamiflu right at the beginning of flu, it'll stop the infection. It works. If you give it later, it's useless. I mean, and by the time most people get to the doctor, it's too late with flu. With COVID, maybe you've got a bit wider window, but we'll see. So we may change a lot of things. We may have all sorts of different technologies for diagnosis. We may have sort of a lateral flow kit for flu, say, that you could you could, the results would be read off on your phone with a QR code that would report them automatically, and then a drone would deliver you the drug. So I mean, there's all sorts of things may change from this, and I hope we'll change a lot of things after this. If we were really rational, and there's no great evidence that human beings are, we'd look at everything through the lens of what happened with COVID. We look at our economic systems, we look at our social organization, we look at our taxation system, we look at how we do things medically. We'll look at things, the medical stuff, we'll do that. But whether we'll do it in a broader sense, because it cuts across too many prejudices and self-interests and all sorts of things. So we'll see.
And finally, Amit asked, some of these questions have been addressed already, but anyway, I will read it out loudly. How often would we need booster doses to maintain the sustained immunity? And the second question is, when planning for booster doses, should we think about designing modified version of existing vaccine, or would a booster with existing vaccine work, like Pfizer, Astrazeneca?
Basically, the Delta variant Pfizer and Mrna vaccines are being made. I think, I'm not sure about Novavax, it's been coming through slowly. I suspect we may be getting a Delta boost next year. There's a couple of variants out there that are of concern. There's the Beta variant, which started in South Africa. It is in various places. It never sort of took over anywhere, but it is more different from the original strain than the Delta. And there's also this Mu variant, which is a bit like that. So whether the worst case scenario would be we got a real immune escape variant where the vaccines don't work against it. We're not seeing that so far, but that could happen. And it's hard to know what that variant might be. There are beta variant vaccines in fact, we're actually putting a beta variant vaccine into trial later this year. And there are some vaccines, there's no reason, of course, why the mRNA vaccines shouldn't have multiple variants expressed in the vaccine. Now, Moderna is already developing a joint influenza COVID vaccine. Now, an influenza vaccine has 4 different viruses in it. So, there's 5 in an mRNA shot. So that'll be part of the way we go. And we hope we don't get immune escape. I suspect all of us, maybe the older people like me may get a booster shot, hopefully not too distant future. We could even boost with the Astrazeneca. Then I would expect everyone will be getting an mRNA booster next year, but I might be wrong. And we may then need variant vaccines. But, it's a bit crystal ball gazing, quite frankly.
You also mentioned the evolutionary perspective. So I think in the long run, the best interest of the virus would be to evolve into a milder form, and this way it could live with us.
Yeah, but this virus has done things we've never seen before. And we've never looked at a respiratory pathogen that's totally novel, highly infectious, and goes right across the planet. But it's done things we've never seen. And one is, it's because it's multiplied, I think, in a virgin soil sense, to cause, in vast numbers of people across the planet. We've seen the emergence of variants which are more infectious and actually about twice as bad, actually. We thought it was hard to really come to a conclusion whether they're worse clinically, but they are worse clinically. The Delta is worse. It's keeping people in ICUs for much longer. And it's a worse infection. It is worse. Not massively so, but it is worse. So we've never seen that before. But think about Zika virus. Remember, there's all this furor about Zika virus several years ago because in the Americas, they were picking up babies that the virus got across into the fetus, and it was causing the birth of a baby that wasn't as it should be. And how much more have you heard about Zika? I mean, basically, I think what happened, it's mosquito-borne, of course, so it was never as much a risk as this one. But I think basically what happened with Zika is basically people got immune. And there was no vaccine out there. They just, large numbers of people became immune. With that class of viruses, the actual percentage of people who get real problems is actually often very small. And so it's no longer a problem. You've got general herd immunity due to infection. Now, whether herd immunity to vaccination will do as well, I think, I do speculate maybe the best immunity you could get is if you if you got vaccinated and then you got infected. I wouldn't advise anyone to try it because you might develop long COVID, but that may be the case, in fact.
Thank you very much. There is another question on the chat from Claire. There is a study done by NIAID showing that intranasal vaccination of adeno-COVID vaccine have much better protection from infection as well as transmission. Do you think we should do clinical trials testing whether a boost of nasally inoculated Astra vaccine will help curb the spread?
Yeah, nasal vaccination. Yeah, it's intranasal vaccination. The idea is you'll get more mucosal immunity up here. And so the mucosal immunity with at the moment is either leakage of IgG in the blood or leakage of IgA that's going through. IgA is a form of antibody that has a secretory piece that gets through a mucosal membrane. So basically, if you infect it up here, your immune response would go on in your tonsils, adenoids, cervical lymph nodes, all that area. And you could either use one of the standard vaccines and puff it up the nose in a puffer, or you could actually use a live attenuated vaccine, which is what has been done with flu. The Russians for years made live attenuated influenza vaccines, which basically they're just passage in culture, so they become milder, and then they gave them intranasally. So yes, we could do that. It might give us better respiratory tract infection up here. But the problem with intranasal vaccines is distinct. When you inject a vaccine at the arm, you definitely know you got it. I mean, you've injected a ml or two of fluid, you've injected that stuff, and there it is. And the problem with intranasal vaccines is you're not really quite as sure about your virus dose, giving it by that route because of all the pathogens, scavengers and macrophages and stuff up there. So I think it's certainly an area that we should look more at. And there are people looking at it, actually. I think there are intranasal vaccines under development. Live attenuated might be the way to go. We don't know, though. We don't know what this virus is doing to the immune system. It's clearly in long COVID, there's an immune dysregulation. And whether you really want to get this live virus in you, if you can avoid it or not, I don't know. I'm still not clear on that. So yeah, there's a lot to be done. I think there'll be money around to do the research.
Many thanks for the answer. Any question from the audience? Please ask your question now.
I just had a quick question, if that's
yeah, of
right.
course. Sure.
I was just wondering, to jump back to the conversation we're having on booster shots with the vaccine. Obviously, we're still sort of somewhat struggling with global vaccine supply, and to some extent, isn't booster shots also taken away from third world countries who sort of we know are significantly less vaccinated? And like, obviously, there's significant ethical implications for that, but also just not providing a fully immunized third world is also just like a fantastic breeding ground for the sorts of immune escape situations that you were talking about as well. So I just get curious about your take on booster vaccinations in that context.
Yeah, of course, there's a thing called COVAX. WHO is trying to get more and more vaccine out into developing countries. As it was, India, for instance, major vaccine producer, India, and major drug producer too. They produced a lot of the AIDS drugs that were used in Africa, and they ended up taking all their own vaccine, for instance. It just wasn't enough to go around. But I think particularly I don't know what we're going to do with Astrazeneca, whether we're going to keep making it. I mean, the Astrazeneca shot, I think it costs about $5, and the Pfizer shot maybe 25 or something. So we've given some of the Astrazeneca away, I know that. We've been giving vaccine away to PNG, the Pacific Island countries. In fact, we've taken on the role of trying to make sure the Pacific Island countries get vaccines. Australia does a lot in the Pacific Island community that we're not all that aware of, and DFAT drives a lot of it. We gave a fair amount of vaccine to Indonesia, I think. So I suspect that Australia's contribution in this will be mainly regional, and Indonesia, PNG, Pacific Islands, those countries. I don't know what Singapore is doing in that sense as well, because they're obviously major players. So that's why I would particularly like to see a major vaccine industry develop here. So we can, when these things come along in the future, we can get vaccines out there much more broadly across the planet. With respect to the ethics of using it in our society as against in other societies, well, you know, it's the main thing here really at the moment with us opening up is to try and stop a situation where our hospitals get overwhelmed. Because what's going to happen if our hospitals get overwhelmed is there won't be ICU beds for heart attacks, for road accidents and all the rest of it. So basically, if you could say, keep older people out of hospital by giving them an extra shot of vaccine, that would be a pretty cheap way actually of, because, you know, it costs thousands of dollars to have someone in a hospital ward, an ICU bed each day. I mean, it's really expensive. We do have monoclonal antibodies. The monoclonal antibodies, the Americans have given them widely for passive immunity. And something like 40,000 unvaccinated idiots in Florida have basically been saved or been given monoclonal antibodies at $2,000 just for the antibody. By the time you add the additional costs of that, you're probably talking about $5,000 of treatment instead of taking $50 worth of vaccine. Okay, now we don't have enormous amounts of monoclonal. The government bought Sotrovimab, which is a cross-reactive mAb, but they've only bought 7,700 doses for the whole country. So people have, we have to encourage everyone to get vaccinated. So among your friends, if you've got any vaccine refusers, beat them about the head, get them drunk, take them off to the vaccine clinic, make the buggers get vaccinated. Because young people will spread it. They're the major spreader. And they're getting sick and they're dying. Some are dying.
Thanks.
Many thanks. Next question from the chat. What is your opinion on using the serum of previously infected or already vaccinated people?
Yes, this is the other, I mean, you know, people who don't have a functioning immune system in our society are given what's called IVIG, intravenous immunoglobulin. It goes under the trade name of Intragam. It's made by CSL. CSL is the world's biggest blood products company. So a little Australian company took over Boehringer Ingelheim. Boehringer works in Germany. Von Boehring is the guy who got the first Nobel Prize for serum therapy of diphtheria from vaccinated horses. Okay, so we now own the plant and the Boehring lab in Germany through CSL. But basically, there's been talk about making an IVIG product from vaccinated people. Now, I don't know where that's gone, whether it's working, whether it was considered to work, but if we're not giving IVIG from vaccinated people or from previously infected people, from the antibodies from previously infected people didn't work very well. It hasn't proven to be a good therapy or good prophylactic. But maybe from vaccinated people it worked better. Maybe from vaccinated people who were boosted, I don't know. But I haven't seen any results or heard much discussion of it.
Many thanks. Next question from Harry. What are your thoughts on the main impediments to Australia developing mRNA vaccine manufacturing capacity?
I think we should go for it. And we've got a lot of talent. There's plenty of people who can do this stuff. I mean, Damien Purcell and Colin Putin and Victoria were, you know, playing around with vaccines 10, 15 years ago, mRNA vaccines. So, you know, there's been work going on here for a long time. And Colin Putin is putting, there's a Monash University mRNA vaccine going into phase 1 clinical trial in December. I think the toxicology studies have been now. No, we're putting a small protein, receptor binding domain protein vaccine in a clinical trial in December against beta. So I think we were lucky that we could actually, in some ways lucky, some ways unlucky, we could actually make a protein-based vaccine because CSL had the facilities. Most countries didn't have the facilities to make any vaccine. It's a pity the University of Queensland one fell down because of their clamp vaccine, which looked very promising. And it could have been made by CSL, but then they dropped it because of cross-reactivity with the AIDS test. it really wasn't much of a problem, and it's a pity because I think it would have been a very good vaccine. And the blood clotting problem with AstraZeneca, it seems to be tied to the adenovirus vector. So we could maybe have avoided that whole thing.
Next question from Tanya. What is the current therapy for COVID-19 patients in Australia, especially if we do not have May maps, as you said earlier?
Yeah, we've got the sotrovimab, which is the cross-reactive GlaxoSmithKline monoclonal antibody. I think it's supposed to work well. It's been approved by TGA or provisionally approved or whatever they do. But we only have 7,700 doses. I hope they've got more on order. But, basically, I think it'll be reserved for people who don't have functioning immune systems. And some of it would be used maybe in people who are very sick. When people go into hospital, they are being treated with that, the drug that was used right at the beginning. I'm blocking on its name. It's okay, but it doesn't do much really. There's a Merck drug, Molnupiravir, which is a nucleoside analog. Looks good, but we haven't pre-ordered as far as I know. It's in phase 3 trial, I think. The Americans pre-ordered some. I don't think we have. So there's really nothing much out there in the treatment range at the moment. A few people will get sotrovimab. A lot of people in Australia have made monoclonal antibodies that could be used therapeutically, but I don't think, as far as I can find out, none of them mean through the initial toxicology study, which you would need to do before you even put them in phase 1 trial. And basically they have to be tried. Monoclonal antibodies, there's always the worry they might be reactive against self. So you always have to do a decent clinical trial. But of course, a clinical trial for a monoclonal antibody, once you've been through phase 1 safety trials, is basically to give it people who've got the infection. So it's a pity we didn't move that forward more quickly. And, Australia seems to lack a capacity for strategic thinking on just about everything, I think.
Many thanks. Questions from Lily. What do you think of the possibility of virus transmission via cold chain transportation? Build on that, instead of live animal stock, could the breakout in Wuhan be a result of viruses hidden in the cold chain product? She also asked,
we thought about it a lot early on. We were very obsessed with washing our hands and disinfection. But mostly the virus is transmitted through air. There was a lot of confusion about aerosols early on, and a lot of rather silly discussion at cross purposes. I tell you one of the reasons. This is classic what happens in science, okay? People are talking about using the same term for something different. So the medicos all said something is an aerosol if it's less than 5 microns. So you've got mucus with some virus in it. If it's less than 5 microns, it's an aerosol. The engineers who design the air handling systems say something's an aerosol if it's less than 100 micrometers. Okay, so there's all this hot air and confusion. Air handling is obviously very important. Potentially, we could catch it from things like frozen packaging. I think there was a hint that might have happened in New Zealand. I don't know where that went. We were all worried about that at the beginning. And with SARS, the original SARS, people were getting it off lift buttons, elevator buttons, and things like that. But I don't think it's probably not the major means of transmission. But I still hand sanitize whenever I can. I go into a supermarket or something.
Russell has a question.
Peter, it's Russell Gruen, the Dean of the College. And
hi, Russell, how are you?
Welcome back to ANU and to the John Curtin School. Thank you very much for a very stimulating hour and a half. I can't let you go without asking what advice you would give to the brilliant young scientists of the John Curtin School of Medical Research today.
Well, I think this is the RNA club. You seem to be in the right area, quite frankly, because I think there's going to be a lot happening in RNA world. And there has been, of course, for some time. It's a very exciting and interesting area of science. And so basically, you've got to find your niche in science, and if you're going to continue in science. And it's always been the case, I think, that at the most, maybe 10, 20% of people who sort of stayed out doing a PhD actually do continue doing science at the level of discovery science. But there's lots of other stuff that needs to be done. We need substantial groups of people with different skills apart from anything else. We need them in all sorts of areas. And I hope we can build a lot more industry here, which is science-based. And there's going to be a lot of jobs there. I hope some of you are entrepreneurs at heart and you really want to go out there and start something and get it going yourself. And I think the climate for that is better than it was, but venture capital has been a bit of a problem. The unadventurousness of a lot of the Australian business community is a bit of a problem. You know, some of them, these people are, to say the least, pretty dozy. But there are interesting people out there and people with ideas and people who will drive things forward. So we got to build that culture too, though. I think it's up to you guys to some extent. And, you know, we have people who are taking sort of business type training after PhD training to sort of help drive this ahead. And it's a big church science now. And, you know, part of the grouping that we meet in our morning meetings that I talked about earlier. I mean, there are people there who sort of diagnosticians who actually were enormously important, getting those, for instance, though we developed the PCR test, we couldn't do all the PCR testing with the state reference lab. We were doing about 2,000 a day and it was killing us. And so basically, one of the big jobs of our people was to get that test out into all the private labs and to make sure that they're doing it right, that it's validated, everyone's on the same page. And all the major testing now is being done in Australia, is all being done by private pathology labs who will send stuff around the country, actually. They have networks, so they're not state-based like the health system, they're national. So there's a lot of stuff out there and all sorts of avenues, I think, that you can think of going into. And I don't think anybody's remiss for doing a PhD in science because, quite frankly, it teaches you to think through from a data-driven perspective. And who else does that? I don't think many economists are actually interested in data. Mathematicians often aren't, so the statisticians clearly are. So I think there are all sorts of things, but you have to be flexible and look. And also, you know, when things do open up again in the US, anyone who's got reasonable command of the English language and trained in Australia doesn't have a lot of trouble getting a good postdoc.
Many thanks for your answer. And the last question for today. So Lily asks, do you think it's possible to develop vaccine for young children? I heard about a COVID case of 2-year-old child.
Yes, the COVID, right from the beginning, it killed some little tiny, some babies with what a Kawasaki-like thing. This is a horrible multi-inflammatory disease that was discovered by a Japanese doctor called Kawasaki. I actually met Kawasaki. We didn't have a very dynamic conversation, but it's this multi-inflammatory problem, and we didn't know what triggered it, but now clearly COVID can trigger this thing. So some died from that. It's very low incidence, but some kids have been dying of COVID. Not a whole lot. They're generally not as severely affected and so forth. But in the US at the moment, they've had major problems with pediatric intensive care units. You know, little kids need to be looked after by pediatricians, not by adult docs. And the numbers of pediatric ICU beds are limited. And what they've had, unfortunately, in the US is they've had COVID, but they've also had respiratory syncytial virus, which is a problem in very small babies. And basically, that's really overwhelmed their ICUs and the pediatric. And a few weeks back, the heads of the big children's hospitals in the US all signed a thing saying, you know, we're really worried. I mean, you know, get vaccinated. So at the moment, the best thing parents can do for their kids is get vaccinated themselves, because if a kid gets infected now, basically, they probably won't go to hospital, but they can get sick and they can be sick at home. So we need the parents to be well and we need them to be vaccinated. The vaccine trials for 11 to 5-year-olds should be through by the end of this year. It'll be very likely that the US will start, providing the trials are good for safety and efficacy, very likely they start vaccinating down to age 5 by January, February. It'll be, I think, a half dose in little kids and an even smaller, they're also doing trials in the infants. So basically the trials are being done. It's very controversial. Some people are very against it, some are for it. We heard some of the discussion earlier in this about the 12-year-olds. And so, you know, it's going to be, we need to get good, clear information out to parents. Pediatricians need to be on board, obviously. The pediatricians, I mean, everyone's agreed that the children come at the end of the vaccination thing because they are the least vulnerable, but they clearly are vulnerable, and some are dying. I think the US so far has lost 400 kids through COVID, that it's clearly due to COVID, but you know, they've lost 600,000 people.
There is a related question for this, so asked by Ivy Chan. While we wait for the trials, what is the plan to protect people who have underlying medical conditions, especially young children under 10?
The medical thing won't go ahead without trials. Young kids could be protected. In the US at least, young kids could be treated with monoclonal antibody. They could be given monoclonal antibody protection. And often you do things in young kids on an emergency use basis. You know, I was head of Department of Immunology at St. Jude Children's Research Hospital for a number of years. And so this is a kids' cancer hospital. Now, kids' cancer is pretty rare, actually. 1,200 kids die a year of children's cancer in the United States. So a lot of drugs that are actually used in childhood cancer, for instance, are used because the kid is just going downhill. So it's a kind of emergency use, pretty much experimental use in that type of situation. So you could protect young kids with monoclonal antibodies, and they're given free to people in the US. You know, President Trump would have been really quite sick with COVID. I think he was well on the way to becoming quite ill, and he was given 8 grams of monoclonal antibody intravenously. And so, you know, that pulled the bugger out of it. I don't know whether history might have been better if he hadn't, but who knows? But, you know, the medics, unlike I trained as a vet. We don't do the Hippocratic Oath thing, actually, but the medics have this commitment to actually helping people. So basically, I think you could protect the little kids with monoclonal antibody.
Many thanks for your answers. And many thanks to our more than 200 attendees, and especially to you, Professor, for coming along. That was a great meeting.
Oh, thanks, and I'm happy to talk to you, and nice to be back at the John Curtin School.
Great.
You know, you talked about the picture of Zinkernagel, and
yeah, definitely.
It's one of me and one of Zinkernagel. In the old John Curtin School, as you walked into the front of the building, it's probably still there, I suppose. If the building's still there, I think. The wing that we worked in is still standing. I remember our lab, tiny labs, ours was opposite the ladies' toilet. But as you come into the building, there was a stairway that went up with bars down, okay? And when they hung the pictures, they were behind the bars. So as you came in, you looked through the bars and you could see me and Zinkernagel, the painting. And so someone who was there at the time, who may have felt a bit bruised by what happened, said, they've finally got those bastards behind bars. So there it is. Yeah. So anyway, great to talk to you, and good luck with.
Thank you very much, Professor.
With how it goes.
Thank you to all. See you next month.
And enjoy
Thank
science.
you.